a little over 100 years ago, a lot of details about the inner workings of an atom were being discovered through experiments. So one of them to discover the electron, one of the first ones there, was using cathode ray tubes and ended up finding the electron. And then another experiment, the gold foil experiment, overseen by Rutherford, but really he's given a lot of credit for the work that his two grad students ended up doing for him. The gold foil experiment found that there was a small dense positive nucleus inside the atom, but evidence for energy levels, which this is called the Bohr model of the atom, the commonly drawn, most simple model of the atom that we would still use in modern time. These energy levels that we would say electrons orbit around on, it's an outdated model, but these electrons would orbit around on. The evidence of that is shown by emission and absorption spectrums. And so what we find, and let's come over here and let's look at this spectrum over here. There's a continuous spectrum of light. But interestingly, if you give an atom some energy, maybe thermal energy, it's a common lab that's done in physics and chemistry classes, is that you have a substance and you heat it, maybe in a Bunsen burner, and then it glows only certain specific colors, only very specific wavelengths come out. The other way with the absorption spectrum is that you hit an atom with some light, or a group of the same type of atoms with some light, and only very specific wavelengths are going to end up being absorbed out of it. All the other wavelengths just pass right by, and the atom doesn't even care that it was hit with that light. That comes from this idea of energy levels. So in other words, basic hydrogen atom here, so that the Bohr model actually works, you have an electron that is on the ground level. And then there are only very specific spots that it could actually end up jumping up to in an excited state. Now, each of these levels is worth some amount of energy, and so the electron jumps up to some spot whenever it receives that amount of energy, or it absorbs, let's say it was with light, some amount of energy. And then it can't live there forever. It's in an excited state. It likes to come back down to ground level. And so then it will return back down to ground level. And if we're actually dropping back down, during that time, it will emit a photon of light out. Now, why it only emits specific photons is because of this energy level idea. It can't emit any photon. In other words, with the evidence showing that only very specific photons or specific wavelengths of light can be emitted, that must mean that you only have very specific spots that the electron can live in specific energy levels. The electron can't live halfway between any of these or any quarter. It's only at very specific spots, and that is the foundation of quantum there. The energy levels are quantized. Now, don't be freaked out by the term quantum or that something is quantized. In fact, you were more familiar, the first way you learned about the world was through the idea of things being quantized or quantum. You only knew 1, 2, 3, 4, 5. There was no 1.2. There was no 1.4. There was no 1.3973. Okay? There was nothing in between. It was 1, 2, 3, 4. Numbers were quantized. Your world was quantized. This is hot. This is cold. That idea of a spectrum actually comes later on. It turns out that electrons still live in that childlike state in reality. They live quantized. They're on one of the energy levels, evidence shown by the fact that we can't get out light from them, the emission spectrum. Whenever it falls back down, it has to release that energy, but except for very specific photons. Now, equations. Energy equals Planck's constant, that's given to you in your data booklet, times the frequency of light. Now, that's both for energy that is absorbed from light and emitted there. So energy that is absorbed, emitted, and the frequency that would be absorbed or emitted. Now, if we would like to, we can also plug in using our equation for a wave. Velocity equals wavelength times frequency. Solve that around for frequency. Right now I got v over lambda equals f. And whenever I plug that in and solve it around for wavelength, I get this bottom equation over here in terms of wavelength. Those two equations are the same with just a very minor substitution. Let's do some basic example problems with this idea. So over here on the right-hand side is a energy diagram of all the different energy levels that a hydrogen atom has, where you have the ground floor with an energy in electron volts of negative 13.59, and then the second, the third, the fourth, the fifth energy level, and then whenever you're at n equals infinity or at the zero energy level, that's where ionization occurs. In other words, the electron has enough energy now to escape the nucleus and escape the atom at that point in time. So first question, determine the number of possible jumps for an electron in a hydrogen atom. And here, we're just going to keep it simple. We're just going to count. The electron starts out at the ground level. And so from the ground level, it could go up 1, 2, 3, 4, 5 possible spots before ionization. And you might think that you're done here, but you're actually not. Because what could happen is it could come up this first jump right here, number 1, up to the second energy level, up to n equals 2, and then receive some more energy on top of that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then likewise, what if it had jumped up to the third energy level on that third jump? 10, 11, 12, and I think you get the gist here. I'm going to go ahead and do the fourth and the fifth as well. So what you can see after you end up counting them all out, you've got 1, 2, 3, 4, 5, and then starting from the second energy level going up, 6, 7, 8, 9, and then starting from the third, 10, 11, 12, starting from the fourth, 13, 14, starting from the fifth, 16 possible jumps here that an electron can go through. And jumping up is the same thing as jumping down, right? The absorption, like the jumping up would be an absorption. If it was falling or coming back down, it would be an emission spectrum there. And it's the same number of jumps either way. For part B of this question, we're looking for both the frequency and wavelength of light emitted. That means that it's falling down. I drew them as jumping up absorptions, but same thing whenever we're falling down. Just coming back down here, being emitted. An electron falls from the third to the first energy level. And so we're going to use the equation here, change in energy equals Planck's constant times frequency. Now, to get our change in energy, this side, I'm going to do the third energy level minus the first energy level here. But these are in electron volts, very small amounts of energy. We're going to need to change this into base units so that we come out base units in frequency also. If you go back and you look at Planck's constant there, we need to be in base units. So 1 eV is equal to 1.6 times 10 to the negative 19th joules. That's from the definition of an electron volt, right? Back to topic 5 here. An electron volt is the amount of energy that you actually have to give an electron, or that an electron gains, whenever it passes through 1 volt there. So it's the charge of an electron is that 1.6 times 10 to the negative 19th. So showing one of these conversions here, right, I have my energy in electron volts, and then I'm going to multiply by my conversion ratio, putting 1 electron volt at the very bottom, and then putting the joules up top. That means I'm going to end up multiplying these two to give me, I need a negative sign on that, negative 2.42 times 10 to the negative 19th joules. And so I'm going to do that also to my 13.59. I'm going to multiply that times 1.6 times 10 to the negative 19th to actually allow me to then substitute in for the change in the energy. So substituting everything in, as you can see, I'm going to divide this over after subtracting these two. Make sure that we have that negative sign there, add the opposite, in this case minus the negative there, and then divide over Planck's constant to get my frequency. And that gives me a frequency 2.91 times 10 to the 15th hertz. Then obviously you can just substitute that frequency into velocity equals the wavelength times frequency, speed equation for a wave, and solve for wavelength where velocity is the speed of light. And that gets you 1.03 times 10 to the negative seventh meters, or 103 nanometers there, just right at the bottom end or a little below the visible spectrum of light into kind of the beginning to turn into the ultraviolet part of the spectrum. Now I'm going to solve letter C actually pretty quickly, but I'm going to go about it in the opposite way. Instead, I'm going to use the equation lambda equals hc over delta E, which remember is the same thing. This equation here is really the same thing as this, just substituting in velocity equals wavelength times frequency in for, right, the frequency there, v over lambda. Put that in for frequency. So I'm going to solve for the wavelength first and then solve for the frequency. This time it looks like we're going from the fourth energy level to the second energy level there. It looks like I need to make a quick correction there, put a 2. So I'm going to plug in numbers and solve. Now, of course, whenever I put in my energies here, and this is minus a negative, right, because you have negative energies, whenever you're dealing with whenever you're dealing with energy levels, because the electron is more stuck to the atom. That's kind of another thing that we'll end up talking about as we go forward. But the electrons are stuck to the atom, so they actually have negative energy there, all the way up till ionization, whenever they would have a zero amount of energy. So minus a negative, but I had to convert these to joules, of course. They are in electron volts using the exact same process we did earlier, right? 1 electron volt is worth 1.6 times 10 to the negative 19th joules. So for my fourth energy level, I did negative 0.85 times 1.6 times 10 to the negative 19th. And then likewise for the second one, negative 3.4 times 1.6 times 10 to the negative 19th to get my numbers. That gives me a wavelength of 496 nanometers, kind of smack in the middle about of the visible spectrum. And then I can use the wave speed equation, right? Velocity equals wavelength times lambda, plug in my wavelength, velocity is the speed of light. That'll let me solve for my frequency by dividing the wavelength over. That gives me a frequency of 6.05 with significant figures times 10 to the 14th hertz here. So the thing that I want you to notice about all of these problems, they end up following pretty much the exact same sort of pattern, where you end up subtracting the energy difference, whether it's a drop or a gain, right? Whether it's absorption with the electron jumping up or an emission where an electron falls down there. And then you're going to use your energy equation. And if you want to figure out anytime you want to get between wavelength and frequency, then you can use the wave speed equation.